Today we're going to pull back the curtain on something called Scada. These are the hidden systems, the invisible network that, believe it or not, is quietly running pretty much our entire modern world.
I mean, have you ever really thought about it? What actually happens when you flip a light switch, or turn on the faucet, or see a train pull into the station exactly on schedule? Well, behind all of that, there's this invisible force at work, and that force is almost always a SCADA system.
All right, so what is SCADA? Well, the name's a bit of a mouthful. It stands for Supervisory Control and Data Acquisition, but the concept is actually pretty straightforward. The best way to think about it is like the central nervous system for massive industrial operations, power grids, water systems, you name it. It's constantly gathering data, processing it, and letting operators control things that are miles and miles away.
So here's our game plan. First, we'll dig into that nervous system idea. Then we're going to peek inside a typical SCADA system to see how it's built. After that, we'll get into the different languages these systems speak, explore what happens when things go wrong, and finally, wrap up with how we try to secure this incredibly important infrastructure.
Okay, let's jump right in. First up, let's unpack the architecture. What are the actual pieces and parts that make one of these systems tick?
At its core, you can really break it down into three main parts, and the analogy is perfect. You've got the control center. That's the brain of the whole operation. Then you have the field sites. Think of these as the senses and the muscles, out there doing the work. And of course, you need something connecting them, and that's the communications network, which acts just like our nerves.
And here you can really see how it all links up. Over on one side, you have that central hub, the control center with its main server. And it's talking to all of these different field sites out in the world. Now, out in the field, you'll see these two key acronyms a lot. RTUs, which are remote terminal units, and PLCs, which are programmable logic controllers. These are the workhorses on the ground, doing the actual job.
So that control center, it's literally mission control. This is where the human operators are, often sitting in front of a wall of screens. We call that the HMI, or human-machine interface, just watching everything. The servers are constantly collecting data, logging it all for later, and most importantly, sounding the alarm if anything, and I mean anything, starts to go wrong.
Now, the field sites are where the rubber meets the road. We're talking about the actual remote locations, a power substation, a water pumping station, a factory floor. This is where those RTUs and PLCs live, and they're wired directly into the real-world equipment. They're connected to sensors that are measuring things like pressure or flow, and actuators that can physically, open a valve or start a giant motor.
Okay, so this brings up a pretty big question, right? It's great to have all this hardware connected, but how does it actually know what to do? What's the logic that tells a controller to shut down a pump automatically if a tank is about to overflow?
Well, the answer is programming. And that brings us right to our next section, the language of control. We're going to look at how these machines are taught to talk and, in a way, to think.
Turns out, there isn't just one language. There are a few, and each one is a tool for a specific job. Let's look at the big three. First, you've got ladder logic. It literally looks like a wiring diagram an electrician would use, which makes it perfect for simple on or off decisions. Then there's function block diagram. Think of this one like a flow chart, where different blocks perform different tasks. It's great for managing a process that's always changing, like maintaining a specific temperature. And finally, you have structured text. This one looks a lot more like a traditional programming language, maybe like C or Pascal. And it's the powerhouse you use for really complex math or algorithms.
So you see, it really is all about picking the right tool for the right job. If you need something simple that a maintenance tech can look at and understand immediately, you're going to use laddered logic. If you're trying to control a delicate chemical process, function block is probably your best bet. But if you need to do some serious number crunching on the fly, you're definitely going to reach for structured text.
Now, all this control is amazing, but it also leads to a pretty sobering thought. These systems are controlling immense, powerful, physical things in the real world. So, what happens when someone else gets control? This is where things get serious. Let's talk about the high stakes of SCADA security.
And make no mistake, this threat isn't just theoretical. It's very real, and it's been growing fast. Just look at this data here. You can see how reported incidents just exploded in only a few years. A huge reason for this is that these systems used to be completely isolated from the outside world. Air-gapped, they called it. But now, for convenience and data analysis, they're being connected to the internet, and that's opening up a whole bunch of new doors for attackers.
And history has already given us some really stark warnings. And we're not just talking about data breaches here. We're talking about real, tangible, physical consequences.
Everything from environmental disasters and massive blackouts to, yes, even serious threats to nuclear power plants. Take this one case in Australia back in 2000. A disgruntled insider, someone who knew the system, used a radio transmitter to hijack the local sewage control system. His attack resulted in over 250,000 gallons of raw sewage being deliberately dumped into local parks and rivers. It's a shocking example of how a digital attack can have a very physical and very disgusting result.
Or what about this one at the Davis-Besse nuclear plant in 2003? A pretty common computer worm at the time, called Slammer, found its way onto the plant's network. Now, thankfully, it didn't cause a meltdown, but what it did do was knock out a critical safety monitoring system for almost 5 hours. Just think about that. A nuclear power plant was effectively flying blind for 5 hours. That's a terrifying thought.
So, the big question is, how do we protect these vital systems? Well, that brings us to our final section, which is all about the modern strategy for securing our critical infrastructure. And it all boils down to a layered approach.
The core philosophy is a concept called defense in depth, and the idea is really just common sense. You don't build one single massive wall and hope it never breaks. Instead, you build multiple layers of different defenses. That way, if an attacker manages to get past one layer, there's another one right behind it waiting to stop them. It's not about being impenetrable, it's about being resilient.
And this is what those layers actually look like in the real world. It all starts with people, having strong security policies and making sure everyone is trained properly. Then comes physical security, actual locks on actual doors. After that, you get into the digital defenses, things like firewalls to keep the control network separate from the regular office network. Then you add security to the control network itself, and finally, you secure the individual devices on that network. You see how they all stack up? Each layer supports all the others.
So we'll end with this thought. From the water we drink to the power that lights our homes, our modern lives completely depend on this invisible world of code and infrastructure. But here's the thing, most of these systems were designed decades ago, built for reliability, not to defend against cyber threats. So the really important question we all have to ask is, as we continue to connect everything to everything else, are we doing enough to protect the invisible nervous system that runs our society?